Hello, my name is Austin Dobrecevich, and I'm here to talk to you all today about my research project, which has been titled The Total Synthesis of 3-Oxyangeloyl Tremetone. So this project and this research was conducted in the integrated lab. Um, I was tasked with a retrosynthetic analysis. And so in a retrosynthetic analysis, you choose a target molecule and then you work backwards and you try to figure out ways that you can make that molecule using easy access, cost-effective materials. And so this is done in industry often to try to create new molecules in more efficient ways. So for my project, I chose for my target molecule this 3-Oxyangeloyl Tremetone, which is shown here on the right. What's cool about this project is that it was found in the roots of this plant called Parastrepia lepidophylla. And so it has a really cool history, and it also has a cool relationship with daisies. So it's a relative of the daisies, and it has been used for thousands of years in the Chilean Altiplano as a traditional form of medicine. So they take the roots from this and they create a medicine that has shown analgesic properties, meaning that it's a good painkiller. And so there are many, many ways in which traditional medicine can inform modern medicine. One of the ways is exactly what this group, Benitez et al., has done, is they look to traditional medicine, they see what they're using, and then they figure out what the active components are in those traditional medicine plants or extracts or minerals, different things like that. And so I chose this molecule because it was found as an active component by Benitez et al. Within this root of the Parastrepia lepidophylla plant. So the 5-step total synthesis that I proposed after my retrosynthetic analysis to actually create this molecule includes these 5 steps. And so in each of these steps, you can see that it's color-coded, and we add specific components to our molecule. And so here is a benzofuran. And so another part of my task in the integrated lab was to create a benzofuran derivative. And so a benzofuran derivative, meaning that it has this benzofuran center group, and then you add different groups around it. And so as you can see, each one of these steps adds a group around the benzofuran main group, thus creating a benzofuran derivative. So retrosynthesis and this sort of analysis allows you to incorporate different groups in order to build the target molecule. So if you can remember from the previous slide, this is the exact molecule that was found as the active component within that root. So now here's a little more detailed. And each one of those 5 reactions that were in the overall color-coded synthesis are now included in this total synthesis. And so this first step is called Friedel-Crafts acetylation. And all that you do is you add this acetyl group. Next, and we couldn't see it in the total synthesis overview because you add the iota group and then it gets removed in the next step. But basically, this is an electrophilic aromatic substitution in order to put this iota group on the molecule. The next step is this really cool reaction called a Sonogashira coupling, which allows us to add this alkyne. So then we can do another Sonogashira coupling in order to add the alkene. So an alkyne is a triple bonded carbon-carbon bond, and an alkene is a double carbon-carbon bond. And there's a sort of intermediate step here that has us deprotect this alkyne so that we can actually add this alkene. Next, we do a ring closing metathesis, which allows us to close that ring and form the benzofuran moiety is what it's called. So that benzofuran, the aromatic 6-membered ring bound to a 5-membered ring. And thus we have our target molecule with five easy steps. And overall, this is the synthesis that I've proposed. And I've only accomplished the first step, and that's the Friedel-Crafts acetylation. Future students in the lab will actually take this and move it forward. And I hope that eventually they get to the target molecule that I've proposed we can get to through this total synthesis. And so what you're seeing here is a mass spectrum from GC mass spectrometry, which is a method that scientists use to prove that they actually made what they're saying they're making. And the way that this reads is you have basically a mass for your molecule that you made, and that mass is what shows up as peaks in this mass spectrum. And so we can see here that this weight correlates to the weight of the molecule that I said I made, and thus I can say, yes, I've made it. Another key aspect to this is that you get fragmentation, and based on specific fragments like this one here, you can get some other mass peaks that correspond to those fragment masses. And so in conclusion, the first step in this proposed synthesis has been accomplished. Optimization of the next reactions is underway, and it's being conducted by other students, and then in the future years will be conducted by those students. So I would like to thank Dr. Farr and the entire chemistry department and the chemistry faculty for creating such an incredible form of learning. In this lab, we're able to truly engage in research-based learning, and through that, we can learn how to collaborate with our fellow students, collaborate with the professors, work between different professors with different disciplines. And so along with that, I would also like to thank the Wigan Foundation for donating the funds necessary to make this lab possible. I am a product of this lab, and it is such an incredible thing. Thank you.